Thank you very much. Actually, we have very limited time for the next speaker. Do we have any question? I can only receive one question to be asked to the professor. Yes, Kazım, please type your question or ask your question.
Hi, Dunning. Can you hear me? Dunning?
Danny, yes, he is typing in the chat board.
Right. Okay. Good to see you online. Dunning, thanks for the nice talk. My question is that what about the pressure in the system when you are studying the thermalization? Do you see any effect of the isotropization or thermalization for the pressure as well, or no? I think he's typing. Okay. Right.
Okay, since Danning Lee is going to answer your questions via the chat board, I think it is better for me to introduce the next speaker in order to catch the timetable of our conference. The next speaker is Professor Dmitry S. Ponomarev from Institute for Theoretical and Mathematical Physics, Moscow. He is going to give a speech on higher spin holography in flat space. If he is here, I would like to introduce him to give his speech. And as I said, if you have questions to Dunning Lee, you can continue to ask via the chat board. Dmitry, this is your turn.
Sorry, can you hear me now?
Yes, we hear you.
Okay, very well. First I would like to thank the organizers for putting this conference together and for giving me the opportunity to talk. And today I'm going to present the results of these two papers, and these are concerned with high-spin holography in flat space. So as usual, let me start by motivating this research. It has two parts. The first part is about higher spins by themselves. So we are interested in higher spin theories, higher spin gauge theories, for the reason that they have rich symmetries and they may in principle provide some toy models for quantum gravity. The thing is that constructing interacting higher spin gauge theories is very difficult, and this is highlighted by very well-known Nobel theorems from 60s, which essentially said that for some natural and general assumptions, massless higher spin fields cannot interact in flat space. Still, like over the years, we have collected some evidence that higher spin theories may exist both in flat space and in areas, but this should be like in some way exotic. By exotic, I mean that they violate some of the standard assumptions that one requires from field theory. So the question is then, how do we construct them? And another question is that, okay, if we violate assumptions, how do we justify that? And how do we guarantee that we don't run into some troubles? And a potential way to answer this is that well, suppose that higher-spin theories are dual to some healthy theories, and that consistency of those healthy theories will justify higher-spin theories. So this argument is similar to what one has in a string theory or string field theory, in which you have a worldsheet description, which justifies consistency. And then once you rewrite it as a field theory, you get string field theory, which is, say, for example, it's non-local, which is something that one would not normally do, but still it's consistent. We know that it's consistent. So this type of argument we want to use for higher spins. Another thing is flat holography. This was the topic of active research in recent years. And despite significant progress, still there are some difficulties with proposing concrete dual pairs. By this I mean that there are two theories which are defined independently, and then they are also related holographically. And we would like to approach this issue using the more restricted setup of higher spin holography. And the reason why we think this is a good place to start is that higher spins are related to very large symmetry algebras, which are very constraining and make things very simple. Yeah, so this is what we are going to do. We'll just try to learn how things work in areas, and then we'll carry over all the ingredients to that space. So in the following, yes, so here's the plan of my talk. First, I will start by giving some simple argument why flat space holography is difficult. Then I will discuss higher spin holography in areas, focusing on representation theory aspects. And then this will be carried over to the flat bulk. More specifically, I will start from chiral higher spin theory in flat space. I will use their symmetries to fix the dual theory. And I suggest this dual theory as the flat space counterpart of a free conformal scalar on the boundary of areas. And then I'll compute correlators in this theory and test them against amplitudes in chiral higher spin theory. And in this way, we obtain a concrete dual pair for higher spin theory in flat space. Yeah, with some boundary dual. Okay, let me start from that argument on why flat holography is difficult. So here is the very basic knowledge from ADS CFT in areas in the usual setup. So the symmetry of areas D+1, the isometry is SOD, 2. And this algebra at the same time is the conformal isometry of CFTB, which lives on its boundary. And then we are interested in two types of representations. The first type of representations are unitary reducible representations of Gelfand-Kirillov dimension equal to D. Let me remind you that that means that the representation space can be labeled by functions of D independent variables. So the reason why on-shell fields have Gelfand-Kirillov dimension equal D in areas D+1 is that the general function in areas D+1 is a function of D+1 variables, right? And then you put the on-shell condition, which in effect removes dependence on one variable, thus you get Gelfand-Kirillov dimension equal to D. And on the boundary side, you have single trace operators, which are just general functions of the coordinates, which means that they are Gelfand-Kirillov dimension D. And the second type of representation that we are interested in, they have Gelfand-Kirillov dimension equal to D-1, and these are relevant for fundamental fields on the CFT side. Why is that? Because you have an extra on-shell condition which removes one Gelfand-Kirillov dimension, so you get D-1. And okay, now we go to flat space, and let me warn you immediately that I'm going to ignore like the difference between BMS algebra and Ponomarev. So for me, it's going to be now that the Ponomarev algebra is subalgebra of the BMS algebra. And like with this command, well, the expected feature is as follows. So everything remains the same except that you replace everywhere SOD, 2 with the Ponomarev algebra in D+1 dimensions. And the problematic point here is this: it's fundamental fields on the boundary. The problem is that there are no unitary reducible representations of the Ponomarev algebra in D+1 dimensions with Gelfand-Kirillov dimension D-1, and which have translations non-trivially realized. Yes. So the last point about non-trivially realized translation means the following. Essentially, it means that the only thing you can have is momenta equals 0. And this is problematic because once you start from representations like that, and you try to construct single trace operators out of them, they will also have momenta equals 0. So they will have trivially realized translations. But this is not true for the on-shell fields in Minkowski space, so this duality cannot work. Yeah, so like putting this like simple, the statement is that there are no natural counterparts for the fundamental field in the dual theory in the fast-space case. Okay, so you have this issue, and you can try to suggest different ways out. What is suggested by the analysis that I will present is that the symmetry of the boundary theory is not just the Ponomarev BMS algebra, but some extension of them. And I will explain it in more details in what follows. So, okay, now I'm going to review how the things work in ADS, focusing on the presentation theory issues. Well, the first, let's say, slide, like very introductory one about very basic and well-known facts. In the simplest setup of high-spin holography in ADS, the CFT in ADS, the boundary theory is free. For example, for 3D boundary, one has free scalar or free spin 1/2 fermion. Because the theory is free, this means that it has a lot of symmetries. So besides U1, the stress tensor, there is an infinitely many higher spin currents, conserved higher spin currents. And these conserved higher spin currents, they generate an infinite dimensional higher spin symmetry. And from the bulk perspective, this symmetry plays the role of the global symmetry of the higher spin theory in ADS. And yeah, you have this large symmetry, higher spin symmetry. And what's important is that it's so large that it essentially fixes both sides unambiguously. So there are different works studying this from different perspectives, but the bottom line is that like symmetry is very, very large, that it fixes both sides, like almost, I'm not going to specify what almost means, but almost uniquely. And in what follows, I will precisely use that. I will give a precise construction which allows one to reconstruct the boundary theory once the symmetry, the higher spin symmetry is known. So yeah, this is one of the ways to implement this. And it's based on the statement that higher spin algebra is the universal enveloping algebra of SOD, which is the idea of symmetry algebra, which is evaluated on the representation of the boundary theory. So okay, this sounds like a bit complicated and technical. I'm not going to explain this in details. So making the long story short, what we are going to do, we are just going to evaluate various polynomials of SOD, generators, which can be done using higher spin algebras, and see whether there are some relations between these polynomials, and these relations are going to specify the boundary theory. Just to give an example, which everyone should understand, is, let's say, one can consider the quadratic Casimir, which is a quadratic monomial, polynomial in SOD, generators, and we know that for irreducible representation, it evaluates a number. Thus, there are some relations between elements in the universal enveloping algebra of SOD, and at the same time, we know that relations like this one, they define representations. So yeah, this is how we are going to proceed. So we'll just look at the higher spin algebra, we will look at different relations of this form, and these relations are going to specify for us a theory on the boundary. So let me illustrate this. Let's say we are in areas 4, and then the higher spin algebra can be written like this. So what we have here, so the star product is just the Weyl-Moyal product between two pairs of spinners. So here, lambda and lambda, so lambda is just a SL2C spinner, lambda bar is its complex conjugate, and we have the Weyl-Moyal product between them. So here, F lambda lambda bar and J lambda lambda bar, they are just generators of the higher spin algebra. And these are polynomials, in fact, even polynomials in lambda lambda bar. So this is how the star product is defined, and the Lie algebra commutator of higher spin algebra is just the star commutator of FNG. And okay, it's also well known that in this form, the S of 3, 2, the ideas for isometry algebra, is generated by these quadratic monomials. So here, J and J bar is the Lorentz algebra, which is split into the self-dual and the anti-self-dual parts, and P are the deformed translations. And as I told you, we are going to evaluate some polynomial expressions and see whether they are related. And indeed, these are related. So one of these is precisely the quadratic Casimir, and you see that it evaluates to -5/4. And this is exactly the value for the boundary theory, which in a given case is a free scalar in 3D. But, well, there are many more relations, and altogether they specify the representation uniquely. And again, like you specify this representation, this looks quite formal, but once you have it, you can try to realize it, and this can be done in different ways. And probably the most standard and most convenient one is indeed as to view it as a free scalar in 3D. Okay, another key fact that we are going to need, so it's a representation theory statement, is the tensor product of two, so here I denote them by RAC, but these are just the representations from the previous slide, which is box phi equals 0, which I also refer to as singletons. So the tensor product of these two singletons decomposes into direct sum of massless higher spin representations. Again, this is a representation theory statement, can be realized in many different ways. The more familiar one, probably the way it's realized in the CFT. And in the CFT language, it looks as follows. So one considers bilinear operators in these free scalars, and the basis in the space of such operators is formed by higher spin conserved currents. So here, like J is the U1 current, this is the stress energy tensor, but then you have the whole tower of conserved higher spin currents, which are dual by holography to massless higher spin fields in the belt. This is the Flato-Fronsdal theorem, but I will also introduce another kind of notation or terminology. So here we have well, operators that construct out of bilinears, they map them to conserved currents, and these operators, I will call them intertwining kernels. They can be also called the Clebsch-Gordan kernels, in the sense that they intertwine representation in the form of manifest tensor product into the form where you decompose it into the tower of irreducible representations. And I'm not going to write them explicitly, I will just use this kind of like Mercedes-like star to show that two scalars get converted to higher spin current. Okay, and then we proceed again using just symmetries. So we start from the two-point function of these free scalars. They are fixed by symmetries. And then considering that the theory is free, we can compute correlators just by doing the weak contractions. So for example, once we compute the correlator of two higher spin currents, we have this Mercedes-like stars here, which convert pairs of singletons into higher spin currents. And the free scalars themselves are just contracted by weak contractions. So these are just weak contractions. And in the same way, we can compute three-point correlators and any number of correlators. And like if you wish, you can go to the language of bulk fields by adding on top of here bulk to boundary propagators. Yeah, and then you naturally interpret this as Witten diagrams or amplitudes in the bulk higher spin theory. Yeah, and this is what they are going to do in flat space. Our starting point is going to be chiral higher spin theories in flat space. These were originally constructed in the light-cone gauge. Probably the best way to describe them and explain what these are just natural higher spin extensions of self-Young-Mills self-dual gravity. So these are also chiral in the sense of not being parity invariant, and also similarly to some self-dual Young-Mills, in the Lorentzian signature, the action is not real. So what else? This theory is also integrable, which means that the scattering is essentially trivial. In practice, this means that endpoint amplitudes with n larger than 3 are vanishing. And this is why that there is no contradiction with no-go theorem saying that the scattering is trivial. And these chiral high-spin theories have been actively studied in recent years. What I'm particularly interested in is symmetries of these theories, and the global symmetry algebra of chiral high-spin theories in flat space can be realized in the following way. As you can see, it's very similar to the one in ADS. The only difference is that now lambdas are commuting, so these are just multiplied with the usual product, while lambda bars are multiplied with the star product, with this non-commutative product. But for the rest, it's very similar. And we are going to proceed along the same lines. So first we isolate the quadratic monomials, and this one would naturally expect that these generate the Poincare algebra. This part does generate the self-dual part of the Lorentz algebra. So from this, we expect it should generate the translations. However, this is not the case. So if we carefully look at how these commute, we will see that these P's, they do not commute. Instead, they produce this L on the right-hand side. And this L is a central element. It commutes with everything. So yeah, this is the first reason why this is not the Poincare algebra. The second reason is that the J, the anti-self-dual part of the Lorentz algebra, is missing. Yeah, but this is what we get from this analysis. And well, if you check the literature, this algebra can be related to the so-called Maxwell algebra. And I will also refer to it as the form of chiral Poincare algebra. So the question one may ask is, okay, like, why is this algebra relevant to the bulk? Since in the bulk we have massless high-spin fields, which are clearly representations of the Poincare algebra, and here I'm like proposing something else. So this may seem as a contradiction, but it's resolved in the following way. First of all, as I told you, this L is a central element, so it commutes with everything. So it pretty much works in the same way as mass squared. So different L's label different representations. And the representations which are relevant for the bulk are those with L equals 0. So L equals 0. With L equals 0, translations commute, so it becomes starts looking like Poincare algebra. So then we need to understand what to do with J. But J, in fact, is also present, but it's just not part of the high-spin algebra. So it's still a symmetry of the theory, but it's just not a part of the high-spin algebra. So in this way, this apparent contradiction is resolved. And like more precisely, the way how this algebra acts on the high-spin fields, massless high-spin fields in the bulk, is as follows. So high-spin wave functions are just functions of SL2C spinors. And so L, as I told you, is 0. And these generators, well, essentially this is the standard realization of massless fields in the so-called spinor realistic formalism, which is used quite often. Yeah, this is a representation that we are going to use for bulk fields. And now let's try to understand what's going on with the dual theory. And as I explained before, what we are going to do, we are going to compute some polynomial expressions and see whether there are some relations between them. And this is what we get. And as I told you already, these relations already define for you a representation. And this representation I suggest to regard as the flat space counterpart of the free conformal scalar field in the boundary of ADS. So at this point it's quite formal, but it would be nice to have some explicit realization of this representation. And again, it can be done in different ways. One of the ways is, well, I give here. So L is indeed central, so it acts algebraically. And as I told you, it serves the representation label that is different L's or different lambdas, they label different representations. And for fixed L and lambda, that is for a fixed representation, the representation space is carried by function of a single variable a, and all the generators act by differential operators. So this is a particular realization of this representation. And then there is also the Flato-Fronsdal theorem in flat space. We prove it by providing an explicit intertwining kernel. So here on the right hand side you have a wave function of higher spins, and on the left hand side this is the wave function for the tensor product of this singleton representation. That's why it depends on A1 and A2. And this is the intertwining kernel, which means that, well, two sides of the equation transform accordingly. And again, I'm not going to write this explicitly, I will just use this Mercedes-like start. This is settled. And now we go to the last thing. In the same way as in the ADS case, we fix 2-point functions in this theory using symmetries. And then, assuming that the theory is free, we can compute correlators just by using the weak constructions. So here I have kind of a couple of pictures showing how the computation goes. Again, you have a bilinear operator in the singletons here, and you have here, then you compute correlators by weak contractions, and then you convert the result into higher spin representation so that it appears as the 2-point amplitude in the massless higher spin theory in flat space. And this is what you get in practice. And in the same way, you can compute the 3-point amplitude of massless higher spin fields in the bulk, and this is what you get. And these results, they match with those in chiral higher spin theory in 4D flat space. I want to note that this is not surprising, as I told you that pretty much everything is fixed by symmetries. What's not fixed is the prefactors, and from this point of view, this computation gives holographic derivation of these prefactors. What I would also like to note is that unlike in chiral higher spin theory, here we are going to have non-trivial amplitudes with number of legs larger than 3. And from this point of view, one can say that this holographic construction provides an extension of chiral higher spin theory beyond the self-dual sector. Okay, I'm going to conclude. So what I discussed today, first I started by reviewing a simple argument explaining why suggesting holographically dual pairs in flat space is difficult, and which suggests that some modifications are required. To understand how this should work, we use the framework of higher spin holography, which is expected to be like a good starting point, as there are very rich symmetries and everything is very simple and essentially reduces to manipulations of the representation theory type. Based on that, we suggested a concrete dual for higher spin theories in flat space, which we regard as a counterpart of the free boundary scalar in area CFT. We also computed correlators in this theory, and we matched them with amplitudes in chiral higher spin theories. So the modification of the usual setup that is suggested is that Ponomarev BMS algebra, should be extended, well, at least based on these arguments. And this extension on the bulk side is not important. It trivializes, well, it's essential for the boundary theory or for the dual theory. And what is missing, so what can be done in future? So thus far it was just the representation theory discussion, which means that we discuss only the on-shell degrees of freedom and the way how they transform under symmetries. And what would be nice to do is to present it as a normal field theory that is have some field that lives in on some manifold, and then we have an action for it, etc., etc. Another thing is that this construction was essentially chiral, and it relies on SL2 spinners, which are perfectly suited for massless fields in 4D, but it's not clear how to extend it for massive fields in higher dimensions. Yeah, so it would be nice to do that, and it would be nice also to understand how this can be extended to parity invariant setups. Okay, thank you for your attention.
Okay, thank you, Dmitry, for this great talk, and questions. Okay, if we don't have a question, let's thank to Dmitry. And I would like to invite the next one. The next speaker is Sudhakar Upadhyay from Department of Physics, KLS, College, India. He is going to talk on